So I'm Sofian Djamaa, and he's Yann Schwartz. We are both from Criteo, working on big data issues and other buzzwords like that. Our main focus, for me, my main focus, I'm working within a team called Analytics Infrastructure, and our main focus is to deliver tools to enable the exploration of all data from Criteo. And Yann is helping us with the infrastructure of all the tools behind, Storm, Hadoop, Kafka, and so on. So just first, a quick overview of what Criteo does is just in 3 words. We buy, so we are an advertisement company, web advertisement company, web retargeting company. We buy displays for clients. We buy displays in publisher websites, for example, Le Monde or whatever. We sell clicks for those ads. If one of you clicks, we get money, and our client pays us for that click. And then we get a lot of money and everyone's happy. But the real thing is that we are not only just buying stuff and selling stuff. We also help clients to optimize their revenues. So it means just like how can I say? We help them to say, with the best ads for the right user at the right time. I think we have a kind of sentence like that I always forgot.
You're supposed to know that by heart.
Yes. I'm ashamed. So yes, we help clients, and with that we analyze a lot of data to help clients to make more money. Allez, you start.
Okay, so we'll start with a very formal definition of what streaming is. Mostly, what is stuff that happens. Mostly you get a lot of stuff happening, usually inside the timeline, and most of the time you're interested in the stream itself more than the discrete individual elements of the data. So working with streaming is not like working with a message bus where a single message are important and you're more working in an RPC context. Here it's the whole flux, the whole stream you're interested in. So what you need to do is to usually you act on that stream and try to aggregate it, transform it, and so on. What's important too, and this is actually can be arguable, but most of the time you have low context, meaning that you can't remember much about what happened before, because the stream and the throughput of the information you get is too high to actually persist everything. So you have a very low short-term memory to process the data. You have a lot of data, related items of data coming in your system, and you have to do stuff on that. So some of the characteristics of stream processing is usually it's always a kind of trade-off, and the trade-off you're making most of the time is you prefer the value latency most of the time over reliability. So it's okay to lose some precision in the calculation you're making. It's okay to lose some of the message. Remember, it's not the individual message that counts. It's the whole stream. What's interesting is that you're not reading just one stream of information, but usually you want to compose different streams and do stuff with them. We'll see some examples in a little while. And actually, the kind of operation you have to do, you can transpose. You have a stream which is many items coming your way in a very short time, but you can see that as an infinite sequence of items. And when you're talking about sequence, usually you have the functional primitives that work well with those kind of constructs. So basically, if you want to transform the items in your stream, you use some kind of map on it. If you want to do joins or to correlate different streams coming in your system, you do zip. And if you want to do aggregation, count the stuff you're receiving, you use some kind of aggregation, so some kind of flow. And it's not a big coincidence that a lot of ways to do stream processing end up having a very functional shape, because basically these are the basic stuff in this processing, sequence processing. So that said, okay, streaming is just a list of events coming up your way. What's the point of using this, or and preferring this to work offline? Mostly is to reduce latency, so you can have a somewhat right result as soon as possible. By position of doing this hours later once it's persisted to disk. You can act fast on things, so if you have a denial of service attack, you can try to detect it as fast as possible and react also, but it's not reactive in the sense of you have one event and you try to react to it. It's not that way. And also, another big use of stream processing is actually copying with basic data. When you have gigabytes of data coming every second, and you have to digest that information, and actually you can't store everything. You have to transform it to a more palatable format and size as quick as possible to save on bandwidth or to save on space. So it's usually those three kind of stuff. So we'll go into real examples, and Sofian will show you a real use case about this. But the kind of things we do at Criteo related to streaming, some of these are already on production, others are more in the pre-production state. But the hello world of streaming is to actually take two streams and try to correlate items together, so it's joined, which can have some interesting issues and can be troublesome. Mostly, the problem is the short-term memory you usually get with stream processing. So you need to match different items in different streams as fast as possible and try to remember them. We also have closed-loop feedback on the A/B testing.
Excuse me, could you please keep the microphone closer?
Okay, I'll try this.
That's a fluctuation.
Okay.
Okay,
but that was on purpose, actually. It's part, okay. You have A/B testing, so mostly we're trying a new model, and we have to just push it on maybe 10% of our servers, and want to try to see how it goes, how it performs. And if we're losing a lot of money, we want to be able to kill it as fast as possible if necessary. So the fancy way to call this is A/B testing. Actually, it's more like testing in production. You also have classic analytics. You want to group by and count stuff, but you want to do it online. You also have some kind of debugging. So you want to follow the stream of, for instance, one new customer wants to see how his ads are served. So we start processing every single message and stream related to that customer, so we can see what goes wrong, and we can have a debugging tool for this. And you also, and we'll see that in the later part, also have ops-related streaming processing. So basically it's not business events, it's not business streams, it's more system streams, but it can be used pretty much the same way. So on the tech side of this, mostly we went with pretty conservative choices. We need to have an infrastructure where we push all the data. We needed to be able to cope with our load. We have something like 2 or 3 million messages a second, something like 2 or 3 gigabytes of data every second. So we need to be able to scale. We need to be able to have failover and to have a nice way of accessing data. So most of the things Kafka provide. And Kafka also have a short-term memory, which is not that short, so you can basically rewind in time to read messages. So it can be very useful when you want to optimize some of our processing. So basically, we push everything inside Kafka, and we have many clients that read from Kafka and do some processing. For the processing itself, we are mostly using Storm, which is a distributed stream processing system based on written by Nathan Mars, who coined the Lambda architecture expression. And also we need to have some frameworks or some ways to unify the way we are actually using batch processing. We've been doing this for 3 or 4 years now, because pretty much everything is done in Hadoop, maybe 6 or 24 layers. So as not to write everything twice, once in online mode and once in batch mode. We like to use stuff that makes it easy to reason on what we want to do and not necessarily write it twice, once for stream processing and once for batch processing. So that's SummingBird. And I let Sofian.
Thank you. Don't think it works. And by the way, sorry for keeping the font. Actually, I like it. But yeah. So as I described earlier on, we help clients to optimize their revenues with the ads on the internet. So we have actually several clients, internal clients, and our real client. They all use the data we transform through Hadoop. That's currently what we do, except from the 2 use cases Yann described that use Storm. But for analytics purposes, everything goes through Hadoop. So the issue is here, they all need the data, but everything has to go by Hadoop. We have all the, I think it's like 500 million events a day that is transformed and stored to have dashboards, to do the billing, because we need money, and internal reports to enhance business development. Business dev is not like people coding EJB or something. It's just like people that try to find out how to do new products or to have new ads, new strategies and something. And our client that uses a web dashboard to see the revenues of his campaigns. So everyone needs that data, the data. And the transformation process basically for each and every one is quite the same. We need to compute the list of clicks, the number of clicks, the number of displays. All those metrics on different dimensions are the same for everyone. So we have one process, but with different constraints. For example, the clients, the business dev and the sales, they need a quick feedback. So as soon as the ad is on the internet, if they can have the first metrics, the number of clicks, the number of displays, the cost, everything, they can react quickly. We have the finance guys, the funny guys, that need consistency, because it's used for the billing. If we say to the client, you owe us $10, and he says, no, on my dashboard it's 5, he wins, we lose. So we really, really need consistency for, actually even for the clients. So it can be applied to the clients, even though it's more or less the case, we try to. But yes, consistency, and so for that we can say we can do everything on streaming, especially as what Jay Krebs said, we can discuss about that later on. But we have this that can be handled only by streaming, even the consistency actually, with the replays system from Kafka. But we have another constraint which really limits us with the use of the whole streaming platform, is the petabytes of data that can be used for replay. We keep every data, every plain data, we keep them, so that if we have a bug or if we have something like that, we need to compute we need to find a new way to compute our revenue. We have to go back to the past for analytics So we need to replay all the petabytes of data that we store. We currently have like more than 20 petabytes, I think. 20, well, 100, 1,000 petabytes. Okay, cool. So yes, that justifies the need of both offline and online mode, batch processing and stream processing as well. We call that basically the Lambda architecture. So in a few words, that's quite easy to understand. It's just like that even this online processing goes by, we have for each batch, a batch is just a unit of time. It can be 1 hour, for example. So each hour, we have a computation done, the aggregation of data done here on the online parts that is stored on a system. And as soon as the batch is ended, the Hadoop part transforms the data. The truth is on the Hadoop part, because that's for our case, because as Yann presented, we have several factors that we can play on to have a lower latency, to have a shorter data to handle in memory. So we can lose events, we can, on this side, it's okay, as soon as we can get the consistency here. And as well, we have the backfilling to handle. So first, data is processed on streaming, and then the truth comes at the end of each batch. So that's basically the idea of the Lambda architecture. And for that, we use SummingBird. What is cool about SummingBird is the platform thing. So it's basically, you write the job, you write it once, and that same job can be executed on many platforms. At the moment, the available platforms are Storm. So you write a job, it's converted to a DAG, a DAG. You can write it, so that's for the online parts. And for the offline parts, you can write it in ScalaIO as well. For Spark, it's not production ready yet, but for ScalaIO, your job is converted to pipes, cascading pipes. And that processing, the job you write is basically doing aggregations. And we can more or less say that monoliths are aggregating functions. So we use a lot of monoliths. And SummingBird as well, so that's a cool thing. And so just a quick reminder for those who don't know what a monolith is. It's just an algebraic structure composed of a binary associative operation. For example, for integer a plus. So 1 plus 2 is equal to 2 plus 1, so it's associative. And it has identity elements for the add. The identity element is the 0 element. What is cool about those kind of properties is that first of all, it enables a lot of parallelism. For the associativity property, we can basically say that you compute things with a linear complexity, you can transform that to logarithm complexity. For example, we can say that instead of doing sequentially all the operations, you can have 2 mappers and 1 reducer to do the operations. So that's the idea. And for the identity element, what is cool about that is when you have to handle a lot of data, you can have kind of dirty data, let's say some null values or something, and the definition of an identity element can just handle each and every case in one single class without having ifs everywhere in your code. To do that, Twitter developed a framework called Aggregation. What is cool about that, instead of using ScalaZ monolith, Aggregation provides only a very, very simple interface, a very simple trait monolith with nothing. But the cool thing is not the trait and all the system around, it's more about the implementation, the existing implementations. The count-min sketch, the hyperlog, all the sketch algorithms. So I'll describe one of these quickly. The count-min sketch is a really, really simple algorithm, really, really efficient as well. You define a set of hash functions, For example, in our example, we have 3 hash functions, W1, W2, W3. So it's more or less, it's hash maps actually. So the first hash map, W1, W2, W3. When you compute a hash function for a given element that comes through your system, you have a value that goes to a bucket, that is stored to a bucket, to one bucket. To get the elements, when you have several data, the idea is to, if you want to have a quick result, you need to store everything in memory. So if you want to store everything in memory, you have to reduce the number of hash functions. And if you reduce the number of hash functions, you can have some collisions. But the collisions are okay because the idea to say how many elements, so yes, I didn't say that, but the count in sketch is to count each value. So if you want to count the number of occurrence of val, you do a get on your hash function, so you get each element for every bucket. When we store it, we do a +1 on the bucket. So when you get it, you just need to take the lowest, the minimum value to avoid all the collisions. So the quick word about hyperlog-log. Hyperlog-log is as well an approximation on counts, but for counting the distinct. Yes, it's a count distinct. We can say it's a count distinct function. As well, everything is stored in memory, very fast and very cool. There's as well the very known Bloom filter. So all those kind of algorithms exist in AggregaBird. Then we computed the data on the platform using the monoliths. We have to store them. SummingBird developed another framework called Storehouse, which is only, let's say, wrappers around any store. That can be, for example, MySQL, that can be Redis, Memcache, a lot of them exist. And it uses the Twitter Future API to be able to query, to have the get and the put methods that run asynchronously. So if we can have a look at the trait, it's really, really simple. You have the readable store that can be used to get an element. When you get the element, you have 3 possible values. It definitely doesn't exist. It definitely exists, and there's an error. And for the writable store, it is the same. So it's kind of a Memcache API, really, really simple. And a cool thing is the mergeable store, which is a writable store, but that can update things. I mean, by that, I mean, instead of erasing the data, you can get the data, use a monolith to compute an aggregation and store everything. Then, as we have a store that uses its own type, for example, Memcache uses an array of bytes. For MySQL store, it's some kind of MySQL value. So instead of putting those classes, those things to the job, you don't want to handle an array of bytes in your job. Twitter developed another framework called Preproduction, which is just a simple conversion between types. So, for example, in your job, instead of having an array of bytes, you can have your own case class. And then you write a projection or an injection, is similar to the mathematical definition, same. So, instead of handling the array of bytes, you handle your case class, you write your projection from case class to array of bytes, you can even use the existing ones, for example, the Java serialization injection, which is quite easy to use, and everything can run smoothly using implicits. So I've been told that if we don't show some Scala code, we can get a good beating, but no hello worlds. The problem is that all resources on the internet are all hello worlds, and from my experience, they don't really show the real issues you can face in production or even in the development, the code architecture. Everything is like, no, the hello world is really, really far from what I will get in the future. So, quick example. Here's the first job I wrote in SummingBird. So I don't know if everyone can see. If it's not really clear, doesn't matter. I'll explain it. But it's like really simple actually. You have two sources of data. For example, we can say for us we have the first source contains all the displays. The second, the clicks. So it's probably badly written. It was really my first job. I wasn't an expert on Scala. I just copy-pasted it. So and normally here is you have to use an implicit, but whatever. So it's really simple. You write plain Scala, and I think that was Alibaba Fast JSON API, I think. So yes. Anyway, you have your tuple, your data. You take all the metrics you want to use, to store, to compute. We do the same on the other source, so for the clicks and for the displays, and then we just have to merge everything. So we create the case class, the key value tuple with two case classes, and the sum is done. The aggregation is done on the monolith, which is only obviously for the value. If we have the same key, campaign affiliate, same client, and same publisher IDs, we can sum both case classes. And it's stored in a store that is passed just as an argument. So it's really plain Scala. It runs on Scalding, Storm, Soon, Spark. Really simple. Then, the monolith looks like this. So, as I said, the trick is like, there's nothing. You just have to override the identity element and your binary operation. That's pretty fast. Finally, you have all the boilerplates to go to configure. So this is for Storm. For Scalding, it's really the same thing. But I've chosen to show the Storm part because I think it has less boilerplates than Scalding. So easy thing, you just have to reference your job. That was the job I showed earlier on. Your sources, here is a Kafka spout, all the list of Kafka spout, because we have two sources, one for the displays, one for the clicks. And then the store, which is this enrich MySQL store. For this store doesn't exist actually because I wrote it, so it's not this store is not available on Storehouse. But I think I'll open source it someday. And it goes to the Storm platform. This platform of T is here. That's the Storm platform. So not a lot of boilerplates. Once you've done that, you only focus on writing the job and writing it in Scala. Finally, for the deployment part, I decided that all the Hello World examples were like really monolithic. Only one project with Storm and Scalding in it. It means that if you do a Uber jar, if you package everything, you'll have to keep the Storm classes when you deploy to a Hadoop cluster, or the Hadoop, all the Hadoop stuff in the Storm cluster, which is quite ugly. So we decided to just split it in a lot of projects. We use SBT assembly to package everything, and the result is one executable jar for Scalding that can be run only by typing Java, run jar, something, the name of the job, classic, and a jar for Storm that can be deployed through an Nimbus. We are currently in pre-production with SummingBird, with some jobs. It runs smoothly, but so I can give a short experience on my experience on all the process, on what I've been through. What is cool is that you write one Scala program that can be run on two platforms, and that's really cool because otherwise we had to write a MapReduce job or a cascading job or a Scalding job, whatever, and the same job has to be written as well in Storm, in I forget the name, in Storm. In a topology. You just have to write your topology. And the problem with that is if you have the same process obviously in two different languages, or even in two different frameworks or whatever, the problem is that you can have some discrepancies. For example, you've added a minus instead of a plus, or just some really stupid things, and that can break everything. So one Scala code for two platforms. The use of monoids, the available monoids are quite poor, and as well some boilerplate is provided. Not everything, as I've shown earlier on, but all the configuration stuff is available in the SummingBird API. And the last thing is that that's a good field to practice a bit your Scala if you're not an expert, or to do some great open source contributions. We have some of them that will be available soon. Finally, for that, the ugly parts. For someone, in my case, I wasn't an expert in Scala, and the problem with that is that the learning curve was, exponential, because even if you are an expert in Scala, you have to go through all the frameworks I've presented. If you use SummingBird, you have to use Storehouse, you have to use Aggregation, you have to use Bijection. So you're like closed with that choice. All those frameworks are really, really cool. I haven't suffered from any problem afterwards. They are really clean, well developed, well coded. It's a great things to use. There are great things to use, but you still need to learn all the things and the plumbering, how everything goes by. And as it's a really, really young project, less than a year, there are some missing features. As I said, in one of the examples, I had to write my own store. It didn't take me a lot of time, but still you need to figure out that, no store, no monoid, no whatever. So. But this is why they need people to contribute to this project. All the dependencies used by Twitter are not up to date. Currently, they are building things against 2.10.3 for the Scala version, I think, or close to that. And when I started using SummingBird, it was on 2.9. I don't remember which Scala version exactly, but the problem with that is that all the dependencies with that, if you want to use the new version of Kafka, the new version of Storm, the new version of this and that, you have to upgrade it. Generally, it doesn't work. You have to do some code to make it work, and that's a shame as well. And that introduces the SBT assembly issues that I had, which is more linked to SBT, Hadoop and Storm, not really to SummingBird. I had a lot of issues with, especially class path issues. That was a real pain. Because I had to package everything. For example, we just take the Storm part. The netty, because SummingBird is using netty, the netty part has to be shipped. But if you ship the netty part, it has to be the same as the one deployed on Storm. You have to write a lot of code in your build.sbt to skip a lot of dependencies as well. My build.sbt is quite ugly. But it's probably as well because I'm not a real good Scala developer. And finally, there's the documentation. If you go through one of those issues, the first thing you do is going to the internet. Unfortunately, for SummingBird and for the other frameworks, Google hasn't the answer. Even Stack Overflow, even Crocbase, even any Chinese real mailing list or whatever, the last page on Google that you have, even that, nothing. You have the tutorials, the wiki, some examples, the mailing list, the IRC channel, the Oscar Boykin and the others are quite cool, so they can help you, but still you need to figure out things on your own. So now we conclude with some insights.
Okay, so we've seen, I mean, regular, respectable stream processing for, let's say, business data, and also we have dark matter in information system. Mostly, you have the real cool data that is flowing, and you also have two other kinds of data you need, but don't have as much importance, as much stringent SLAs on it. So mostly you have logs, all your applications are spewing out logs all the time, and you need to be able to process it. And also all kind of metrics, mostly system metrics on all your servers. At Criteo, we have something like 8,000 servers. We have 1,200 nodes Hadoop cluster. So everything keeps pinging and sending data, and also writing gigabytes of logs. We write, it's not for bragging, it's to give an idea of the scale of the log we have to process. For Hadoop cluster, we write something like 12 terabytes a day of data, and for those 12 terabytes a day, if we enable info logging in all our Hadoop cluster, we have 2 terabytes of Hadoop logs a day. So basically 10% of the data we process are logs. So we can obviously keep all those data in the same way we keep the business data. So we have to do something about it, and we can also work. So basically, we can work on the logs and work on the metrics. So metrics, we also have metric system, graphite, ganglia, pretty much whatever, and we have a lot of dashboards. But some of the rules and some of the visualization we need are not easily expressed as just a rule, just a threshold. For instance, sometimes you have systems of 3 or 4 servers together, and we need to have an idea of the quorum, how many are up, how many are pretending to be the masters. Last week I heard someone that said that we actually had a split brain from some backup stuff, and it was supposed to be something that was normal. We need to be able to see, okay, I had 3 different events from 4 different machines in that range of time, and I have to raise an alert if only one is actually responding. It's not easy to express in graphite. We also have contrived conditions, and also we need to have synthetic metrics. So basically what we did with the streams of data, we'll have to do with the streams of metrics. So we get a metric from part of the cluster on the storage side. We need to have metrics on the network throughput, and we need to be able to see if we'll be able to ship all the data throughout our data centers. So basically, we're storing the information in graphite and so on. We need to be able to do complex event processing on those data. So for this, Storm and Kafka could be a little bit overkill. Kafka, because we don't necessarily need to store all the data and to have reliability on our data. Storm is a lot about custom development, and also we need to be able to, we have an SLA on our regular stream processing. So there's a very interesting event processing framework called Riemann, which is written in a very interesting language called Clojure. Mostly it's like, it's event processing and stream processing on a single node. So it doesn't, Kyle Kingsbury, who wrote Riemann, knows enough about distributed system not to try to do that. So you have single instance, and basically what you do, looks like any program, you have inputs and outputs, but mostly you have many things coming inside your system, inside your single host. Usually it could be usually system metrics, but actually some people use business metrics to do it. So whatever you get with your graphic, ganglia, Mooning, whatever, you get in Riemann, you have some rules and actual programs, and since there's no persistence, you do whatever you want. You can send message and send text or persist it. And actually what's nice about Freeman is the way, instead of having DSL or whatever, you actually write closure code. And like I said before, a functional approach to stream, so basically you work on sequences, is perfect for those kind of language. So basically you can filter, or you can, you can have a filter, you can specify a duration where you want to remit the messages, and basically you join streams, you work on them, and you define rules. What's interesting with Riemann being written in Clojure is that it's easy to dynamically change the rules. It's easy to use a remote REPL to just look at what's coming inside your Riemann server and try to do some debugging. So mostly it's single hosted event processing. It can go up to 20 to 30,000 messages a second, which is not that bad. And basically we're not using this as a graphite, because we do have graphite. We're using this as ways to look at our cluster different ways. So especially our Hadoop cluster, we have several issues, mostly how to get information about the current state of a cluster. It doesn't help at all to have 1,200 different graphs telling how much CPU you have. It doesn't tell you anything. It doesn't tell anything to do an average of those 1,200,000. So basically we need to have a feel of what happens. There are two things, those are a bit, so if you don't like Clojure, maybe you'll like this better. Mostly I told you about having 2 terabytes of logs a day. What we can't actually store them, even with using Elasticsearch for storing logs, but those logs can't be used in Elasticsearch. So basically what we need to do is to transform something which are logs into something which are signal, which are metrics. And one way to do that is to say, okay, someone somewhere called log4j add a string template, put some values in it, and then wrote this in a file. We actually don't care about the values. We get stuff like this. And what's important when you're actually processing your logs is you want to see if there's an error somewhere. You don't care about the line number, you don't care about the numbers with the message. What you need is the actual message. So basically you have to reverse engineer the string template in your log. So this is the pseudocode to do that. On your one of your nodes, so you have 1,000 of nodes, you just look at the log, you cut the timestamp part, you get rid of anything which is pretty much customized for your log. So basically you try to normalize, to canonize your element, and you aggregate this. So you're not actually doing this, but that's the idea. You aggregate this, so now you don't care about the timestamp. What you need to do is I had this exception, this security error 1,200 times in the last minute on that node, which happens a lot with us. You send that, and you get a metric, which is this kind of error at that time, how many times. And then you aggregate it anyway. Also, what you can do instead of this, now that it's normalized, you can have a SHA-1 of this one, and you just send the SHA-1. So you have 2 kilobytes log entry, and now you have a few hundred bytes. So now you can actually process your 2 terabytes of log a day. So basically what you get is you get a global vision of what's happening in your cluster. So you can see that there are this error message on every cluster. You can see that only the data nodes which are on that track are having this issue. Or you can say that, oh, I'm having a quota problem with some user. So basically you can, you're using the logs, you're actually reverse engineering the logs, which are pretty much useless, actually. When you have 2 terabytes, it's like you have nothing. And you transform the logs in signals, and then you aggregate them, and then you can visualize and work on them. So basically this is a way to use logs, to transform logs into metrics, and to use stream processing to be able to act on them and to actually visualize what's happening on the cluster. Okay, we could, this is actually something we're developing and will hopefully be open sourcing sometimes in the future. So there are a lot of things to say about streaming. What we wanted to stress here is how we're using it. We're not pretending it's the only definition of streaming. There are ways to make streaming extremely reliable, but like the keynote said, you always have to make trade-offs. So we usually take the stance of, okay, it's okay to lose some information. We will still be recomputing everything in offline mode later. But you can build a system, a streaming system, which is pretty much reliable. There are ways, the difficulties we're running into now that we have many streams is to actually have a topology, a way to know what's actually streaming in your information system, and how can you fork it, and how can you declare what you want to do with your streams. And last, we're hiring, so if this sounds fun, it actually is most of the time. So come and see us. Okay.
Yes, you can just talk to every person that wears that kind of ridiculous t-shirts. And I think it's Notorious BIG for Notorious Big Data. So yes, you can talk to any one of us if you want just to discuss about this, or if you're interested in being hired or whatever. If you have questions.
Okay. Yes, thank you first. When dealing with streams, there are certain operations that you mentioned that involve time, like joining two streams over time windows. My feeling is that this is very different semantic from the one you have in the batch layer of the Lambda architecture. How do you fit those together? How does the batch layer handle time?
You have to make assumptions. So basically, you can join anything with everything. So usually, it's a matter of having a time window where the stuff you try to correlate happen more or less in the same time window. What helps is that you can actually, using Kafka, you can actually rewind in time. So you have a little more leeway. You're not constrained by your memory. But it's not easy. You can't actually say, if something happened 5 days ago and something happens again now, it's really hard to do this in a streaming way. So basically, that's the short-term memory problem I mentioned. So you can have off-heap memory, like a key value store for storing what you can't have in the process itself. But it's not something that can be solved in any case. So there are many ways to, and sometimes it's not possible to do any joins using a streaming process.
Are you? Yes, running late. Rephrase it a little bit. Are you using the same time window, time ranges in the batch layers?
Yeah, for the bucketing, the batch he was mentioning, we're using, so we have results for 1 hour batches. But when we do the processing offline, we actually do whatever we can. Usually it's, the coarser grain is 1 day or something like that. Right, so?
No, actually it depends because, yeah. No, actually it depends because it depends on your source. For us, the files goes, some aggregation can be done each hour. Some no, for the daily aggregation, obviously you need to have all the hours. But for some hour aggregations, like the number of clicks or displays in an hour, within an hour, we keep the same batch for Storm and for Hadoop. Exactly the same. The constraint comes from your source and comes from when the events are going, and obviously for your store, like if you want to compute an aggregation, in which time window you want this aggregation.
Another question. One last please, before everybody goes to lunch. And then how do you handle the case where the input stream is so important that your hardware or your can't handle it? You run out of memory, out of CPU.
You mean, for example, if you have the same amount of data in Storm and in Hadoop, but in Storm the amount of data gets really, really big, so that we cannot handle it in memory. Is it your question?
I'm talking about the live stream, the one that you can't control.
Normally, that was the last point of Yann. It's we keep on measuring things to try to avoid that kind of thing. But if it happens in production,
that's also if you are able to partition your data. So if you basically model it, so you can compose your results, and be able to route everything relating on the heap and many things working on it. Our main problem with bandwidth is actually we have many data centers and all the central data is on our Hadoop cluster in Amsterdam. So basically we're limited by the bandwidth between our data centers. That's our limit we're running into. We can scale anything, we can anyway buy 100 servers, but we won't be able to break that barrier. So that's our main key factor. And in some cases, we can't do that. We say, okay, this won't be possible with streaming work.
Yes, and the fact is that this kind of answer we give is, as Yann said, mostly due to bandwidth constraints. Because we just have to add nodes, we have more memory, we can handle more things.
Okay, thanks guys.